Hi, and thanks for listening to this talk. My name is Pascal Gautron. I'm a senior DevTech engineer at NVIDIA, and we're going to talk about ambient occlusion in massive CAD scenes. Ambient occlusion is a very simple approximation to global illumination, in which the estimated incoming lighting at a point is only a function of the distance to the surrounding objects. The more surrounding objects at close distance, the darker the point will be, and the less surrounding objects, then the brighter. This has typically been approximated in screen space in real-time applications for years now. And the idea is, instead of actually looking at which objects lie above a given point, then we simplify the scene by just considering it as the Z buffer. So we just have a 2.5D representation of the scene, and we compute ambient occlusion from that. This kind of works. It gives an idea of ambient occlusion. However, it's missing a lot of details, especially because this 2.5D representation, of course, misses all the depth complexity of the image. So we end up with halos, for example, or some missing shadows. It would be more interesting to use ray tracing, where we can have access to the entire scene. But if we want to do that, we need to trace a number of rays in the scene for each visible point. And that means that when we don't have enough rays, then we have noise in the image. We could say, no problem, let's denoise it. But then denoising happens in screen space, so we end up with the same or nearly the same problems as we had with the SSAO. That is, we are going to filter using some kind of glorified bilateral filtering using our 2.5D representation of the scene. And we end up with some overblurring, losing details in general. So ideally, we would like to denoise in world space so that we can still preserve all the depth complexity of our scene. So that's where we started. And we also had a number of additional constraints, one being the complexity of the scene, that we would have to deal with massive CAD models. So think 100 million plus polygons. Those CAD models typically don't have UVs defined. They can have arbitrary high frequency. So for example, very complex mechanical models. The scenes can be fully dynamic because in a CAD viewport, everything can be edited. And it's really important that the rendering is fast and consistent with the model because this AO will be used also to make design decisions. So if we want to denoise in world space, it means we need already to be able to sample in world space. So we've got a few options there. Typical ones include UVs, but for that, we would need some paintable UVs defined in the entire scene. And on top of that, paintable UVs that have minimal distortion. That's something that absolutely does not happen in the CAD world. Since those CAD models have very dense tessellation, we could think also of storing AO at vertices and just using linear interpolation. However, in some places, we may end up with a lot of vertices in one pixel, while for some other places, we can end up with big slivers of of geometry that triggers all those artifacts over here. So we don't want that neither. A more generic approach is the one that's used in the RTX-GI SDK. The idea is to have a uniform grid of light probes. And those light probes are updated in real time, and they're used to light the geometry around them. This works fine as long as the grid is defined properly depending on the scene, especially on the scale of the scene. And we still end up with some probes that are, for example, standing in midair and are absolutely not contributing to any point in the scene. Some probes that will be stuck inside geometry. Those ones really need to be discarded, otherwise they would trigger some artifacts. And more importantly, if we have a scene that has very different scales, for example, imaging a complete city, and we can zoom in and zoom in and zoom in to a bolt in a car parked in that city, then a uniform resolution absolutely cannot capture all the details that we would need. Instead, we decided to turn to spatial hashing. The idea of spatial hashing is very simple. It's borrowing the general idea of hashing is using databases and so on, so that we can take some input data and hash it into a single hash key, and then we can store data in a 1D array at each hash index. So that's here, for example, some hash cells for regions of the scene. So it works exactly like that. Starting from a point defined in n dimensions, we can apply an n-dimensional hash key, hash function that will yield a hash key, typically a 32-bit hash key that will give us an index in an array. And there we will store a second hash key that will be used as a checksum to really identify the point we are talking about, and some arbitrary data about the lighting at that point. If we have a second point, then we can also hash and obtain an index, store checksum, and its data. As with any hashing scheme, we end up also with collisions. So, for example, a third point may collide with the first one, and that's where the checksum comes in. Then we will evaluate the checksum also for P3, see that it's different from the one of P1, so we know that it is a collision. Then we can do a linear search to find the next available slot in the hash map. So how do we hash a 3D point? We can do that very simply by choosing one 1D hash function, for example, wang hash or a XOR shift, for example. And we can first hash the first component of our point. Then we add the second component, hash everything together, hash the third component, hash everything together, and we have a 3D hash function. If we do that naively, just by taking the bits of the floating point coordinates of the of the point, then 2 points, even if they are really close by and very related, then they will have different hash keys, which means we won't be able to filter those together to be able to smooth our signal in world space. To avoid that, we need to resort to discretization. So if we discretize all our coordinates, for example, with the discretization step S, then we will end up with the same hash key for 2 points that are nearby. Now we have the question how to determine this discretization step. In this trivial case, we could decide to have our discretization step matching the size of 1 pixel in the final image. So this would work fine, but in a dynamic context, then we may zoom in this area, and then the discretization will be too big, yielding some discretization artifacts. To avoid this, we take inspiration from the MIP maps, and basically we have a log scale of discretization steps, and this is only driven by a target pixel size for the cells and an arbitrary minimum size of the cells, so that can be safely put to float min or whatever small constant. It's really irrelevant. Then if we do that, we can be far away and have a discretization step that matches our pixel, and then move closer and adapt our discretization step, and so on and so on. So to include this in our hash function, then we need to make it 4D, because we will discretize with our adaptive discretization step, and we use this step size as LOD identifier, if you will. So we'll also hash that on top of the 3D coordinates. The surface orientation is also very important. If we have 2 points that can be very nearby, but with opposite normals, they will have completely different incoming lighting information, so we don't want to filter those together. Then we also integrate our normal to the hash key, for example, by discretizing each component of the normal and also hashing those 3 components together. A last dimension is related to dynamic scenes. If we have modifications in the scene, then we may not want to reset the entire hash map every time. We may want only to regenerate some parts of the hash map, or we may also want to keep information from several frames inside the hash map. And that's very easy to do. We just need to also add a frame identifier in our hash key, so that we can even have some samples of the same point at different times that are available in the same hash map. Since the hash map has a limited size, then we also need to eliminate some data at some point. For example, when we navigate here, we only see this point P9, and we navigate around, we see a few more points. And at some point in the navigation, the search window is completely full. We have collision that we cannot solve. Here, if we just drop that point, then we won't have any lighting information, and that will trigger some visible artifact. So instead, we also store the time at which a cell was last used, so that we can detect that, for example, this point P9 hasn't been used since the very beginning of our navigation. It's not visible anymore, so we can safely discard it and replace it by the one that we actually need in the current image. This elimination allows us to guarantee that we are never removing entries that are used in the current image. So, in a nutshell, to allocate cells, if we start from a deferred shading approach, so we would have some positions and some normals in some buffer, and then we can compute a hash key from those positions and normal. Then, if there's an entry present for this hash key, we can compare the checksums. If they're the same, then it means there's already a cell at the location of our point, and we can just use it. If the checksums are different, then we either discard whatever exists if it's too old, or we do a linear search to try to find the next available entry. And if there's no entry present at all, then we create one, initialize everything, and output the cell ID. Since we're able to manage several levels of detail, we are storing information at also several levels of details at once. So when we allocate cells, we do it at the target LOD, but also for 3 coarser LODs. And we'll see a bit later what we'll do with that. Now we have positions, normals, and the cell ID for each pixel. So from that, we can sample a number of directions, trace rays, and add lighting contributions to our data in the hash map. So if we do that naively by just taking a random sequence for each shaded point, we would end up with a proper sampling of each hemisphere above the points. The more samples we add, the more it will be converged. That would work. But if we think at the meaning of a hash cell has a location that is pretty limited, and also the normals are very similar. So we can imagine some kind of global hemisphere above a hash cell that we want to sample. And if we sample each point completely independently, then mixing all those random sequences together may end up with some very suboptimal sampling. Instead, we decide to use the same quasi-Monte Carlo sequence for each cell, so that we can pick some elements of the sequence for each point within a cell, and we can guarantee that our global hemisphere of the cell will be sampled optimally. Now, if we compute our ambient occlusion at a given point, and we move back, for example, then we will still see that point, but at a different level of detail. And then we would need to sample again the incoming lighting at that point, although we already did it before at a finer resolution. So instead, what we do is when we compute the AO at a given level of detail, we use the fact that we compute several levels of details at once. So we have several cell IDs for a given pixel. And then we propagate all this information to the coarser levels of details. Like that, when we move around, we can reuse already some data that will be present in the hash map at those coarser levels of details. So it's dramatically reducing the artifacts, especially um, popping artifacts, completely disappear. And then we can continue to populate again at higher level of details. Once we have that, we can estimate our ambient occlusion simply by fetching the information that we've been storing during the ray tracing. So here we've got the number of rays that actually don't hit anything and the total number of rays we traced. Divide one by the other and we get an ambient occlusion value for each pixel. Just doing this, however, if we've got not that many samples, we still have some noise. So instead, we also leverage these multiple levels of detail and we use it to fetch some additional virtual samples, if you wish. That is, when we fetch our data, if we don't have enough samples, then we fetch information from coarser levels of detail, add their contribution until we have enough samples, and then we can again perform our division. And finally, the spatial hashing is very convenient, but it does not allow us to filter easily because two cells that can be nearby in world space can be completely in different places in memory. So if we start trying to do some filtering, then we are trashing the cache and the performance really degrades very quickly. So to remove blocking artifacts due to the nearest filtering, if we talk in texturing terms, then we use here a screen space filter that's just used to smooth out those boundaries. And they're used with a similarity metric that uses the same criteria as the hashing. So same location, similar normals, and so on. We do that during using an approach that's very similar to what Christoph Schied and colleagues proposed with SIGGRAPH using atro sampling. So if we put all that together, we start from our gbuffer. We can allocate cells at several LODs. We can retrace while propagating to all the LODs, estimate the ambient occlusion, and finally filter it in screen space to get our final result. Our first test is an architectural scene, so with around 50 million triangles, so moderate complexity. And in the very first frame, the cost is really dominated by ray tracing because we need to trace a lot of rays to have a result that's not noisy. But then when we navigate, we have mostly some work to do in parts that are just newly visible, new LODs that are visible, places that get unoccluded. So we can really focus over there and reduce the work in the areas we've been already seeing. That allows us to really reduce a lot the cost of the ray tracing during navigation. In this other architectural scene, we can also navigate within a 5 milliseconds budget, so that makes it even VR friendly. That scene is an actual CATIA scene using more than 200,000 instances. Server scene was kind of our crash test because it has more than 300 million polygons. And in the first frame also, the ray tracing dominates, of course. But during navigation, we can still leverage a lot of pre-existing information, as you can see here. So we can still navigate in a very low budget. And this test is here to illustrate how we can still preserve the very fine geometric details. Here, an SAO algorithm wouldn't be able to fetch much information from this because all the depth here would be only noise. But using ray tracing and spatial hashing, you can see that all the details are nicely preserved without overblurring. This has been implemented also within the CATIA CAD modeling package, and it's been demonstrated on a fully detailed Renault Dacia Duster with more than 10,000 parts. And this is the illustration of the integration with the full model. In conclusion, we propose a very simple technique that allows to compute ambient occlusion in dynamic scenes at very high frame rates using ray tracing. In future work will include the computation of IBL shadows, extending to full GI, also multi-GPU for further performance. And I would like to thank my colleagues at NVIDIA for supporting me in this work and making all that happening. And as a final word, I would like to dedicate this presentation to my dear friend Yaroslav, who passed away last December. And I would really encourage you to watch our course about the legacy of all his research work. Thank you very much for your attention.